So here we today we'll talk about the geometric structures on 204. So using charts and the goodness of the geometric 204s. So geometric 204s are always good, and then we use development pair and then the expanders and the flat expanders and the transversal section. So there's a different way to see this, what the orbifold is, geometric structures on orbifolds are. So what we are going to do. So these are some references. So please see these references here. Okay, so we want to define what the XG structure is. So XG be a pair defining a geometry. So G group, G is a Lie group acting on manifold X effectively and transitively. So sometimes you can drop these, but usually you want these. So given a manifold M, there is these three ways to define XG structure. So first using the atlas of charts, and then the developing map from the universal covering space and the cross-section of flat orbifold expanders. Okay. So atlas of charts approach. So given atlas of chart for M, so M is an orbifold structure, so you get some UK fee. So there's a chart from so you find the X chart row from this U to X as a homeomorphism, and then the homeomorphism to an open set, and then there's a injective homeomorphism K to G. So this Lie group, so that the row is a equivariant map. So it commits with so the actions is preserved. Okay, so that's first what we want to have for each chart. So some of these chart you want to have these atlases. Okay, and then you have an embedding. So for each embedding, UH side to UK V, where B has a chart like this, and then of course this has this chart. So you want this embedding to be always equivariant respect to this injective homomorphism, which is going from H to G. So this right. So it has some H prime, which is injective homomorphism, and then the point is that so this row will commute with this. Right. So the point is that this V to U will respect there will be induced homomorphism from H to K, right, as well, and then so you will have a H goes to K, and then these three things has to commute, right? So that's so then the point is if you have row circle I is going to be some C times rho prime, where H prime has to be this. Okay. So it doesn't commute. Sorry. So it commits up to maybe some action by this G. Okay. So that's what we need. Okay. Okay. So if it's commit, that's fine. But if it doesn't, actually, it's differed by some G element here. Okay. And so this is a way to identify some GX structure is being preserved. Okay, so that's what the is. So we simply identify open subsets of X. The above signifies greatly, and I is a restriction of elements of C, and then the I ties conjugation by. So sometimes you can just think of U as a subset of K X. Okay, and then this will then I just is an inclusion, and then I just can be just the restriction of element of G. So you don't have to talk about this row. Row is being inclusion. So then that's an easier way to understand. So if you think of U as some subset of X instead, and then V as subset of X and so on. Okay. So once you have these atlas of charts and then any inclusion, any embedding satisfy this property, then that gives you an XG structure. Okay, so you have this structure, and then the maximal such X chart is called the XG structure on this. Okay, for each chart, I don't think you need each chart, but so for an atlas, for each chart you need for a given atlas you have to have this. Okay, I don't mean all the charts will have this property. Okay, so that's a thing. Okay, so that's how you define a XG structure, sometimes GX structure, and so now the XG map going from M to M. So suppose we have this is XG manifold, N is a XG manifold. So at the moment you only want this to be the same dimension, okay? Because we don't really have any other definition yet. But of course you can extend this definition. But of course the problem is that maybe authors don't agree with this. So that for each X, you go to point Y, and then there's a chart, UK psi, and then VH psi, so, P and then psi, so that F sends this image into this, and this will lift to some F tilde, U goes to V, such that rho prime is F prime circle G rho. And then so this up to so when you project to X, they differ by some element of G. Okay, so H now become H prime I star is some conjugate like this. Okay, so that's what the XCM map is. So XCM map means that for each point you can find these two charts with these properties. Okay. All right, and right. So one point is that this F tilde may not be completely unique. Okay. So there's some really bit of ambiguity, but so you choose. So usually you want this F tilde to be set in the information of XG map itself. Okay. So that's what the proper definition should be. Okay. F tilde is already being in the information of this map. Okay. But of course, app tilde is only defined up to some action by C as well. But that's really up to some. So you could change this. I mean, maybe you can change by up to some action by H and K. That's a bit of ambiguity. So I'm just saying that there's existence here. I'm just saying there exists such a thing. Then it's called smooth. Okay. But it may not be uniquely determined actually, right? So, but of course, some orbifold theories should decide which one they want to do. But of course, um, yeah. So, in of course, the groupoid people knows the exact definition. So that's they have different. So in other words, F is a restriction of element of G up to charge with homomorphism induced by conjugation by element of G. So when you think of this U and V as a subset of X, instead of doing phi and these things, then this just is a F tilde just will be some element of G, and these H will just be a conjugation. Okay, so that's a better, simpler way to see this. Okay, okay, right. So I mean, of course, in the groupoid picture, these are all very well defined, but only for people aren't really completely determined. So atlas of charts approach, XG orbifold is always good. So that's a theorem of Thurston. So why is it always good? So that means that this orbifold is always covered by manifold, but so that's why some people just want to not study orbifold because they say it's always manifold up to cover, so you don't need to study this. And so that's the argument against studying orbifolds, of course, yeah. But of course, those are all political, I think, not real. There's no real substance to it. Uh, So there are lots of politics in mathematics too, right? So basically build a germ of local XG map from M to X. So you have some XG map. So you want to consider a germ of that. So that means that you want to consider a smaller and smaller set and the restriction of that map. Okay. So this is actually going to be a principal bundle and manifold. So for each of these model pair, you want to look at germs defined at phi u, and then so what that germ is you can identify with this. So it's going to be u times g times u multiplied by k. So k will act on u usually, and on g as a right action, I guess, right? On the right, because this is a map. So okay, you can think of it as a map. So you want to consider that as a pre-composition map. Okay. So k acts on u. Okay. So this g will determine only up to this. But anyway, so you need to identify u as a subset of x as well. So that's one thing you need actually, right? And then you can see that this is really this. Okay, so I'm not completely proving it, but you can identify with this. And then the projection is just induced by projecting to u. Okay, okay, so or you should say projecting to u mod k. Okay, so that's probably better. Okay, and then you can paste these together to get GM. So phi sub u is just u mod k. You can think of u mod k, and then these things are glued together to get manifold M. So once for each u, build a G times u at K, and then you can glue these together. Because there for each embedding, you can always leap to a map from G times some W go to G times u, and then you can well define these things. Okay. But G mod M is a manifold because K act on this freely, because for course, for U it has a fixed point, but for G it's never going to be free. So you have any fixed point, then over that the G will not. So K will act not trivially on G, because so if you think of U as a subset of X, okay, because G acts faithfully, right? And so then you glue these together, then you get a manifold, and then you have this foliation given on this set because you take any G0 in G, and then you times U, so this will give you a foliation on this. And then K will act preserving this foliation, right? So M will GM will itself will have some foliations of dimension equal to same as M. Okay. But these are manifolds now, okay, because these actions will never act on fixing any points of these. Okay? So these are going to be all manifolds. So each of the leaf will cover M. Okay, so this is a manifold covering M. So since this is and of course this leaf of this foliation will go to leaf here. Okay, whenever you do the embedding, right? Okay. So therefore you get a manifold covering this XC OV4. Okay, but this is not a finite cover, it's just a cover now. Okay, so we don't have the finite cover. But if G is a subgroup of sorry, there's no R here, but the subgroup of a linear group, then G is very good by Selbach lemma. So there's a Selbach lemma which says that if you have any discrete any a linear group, then you can find the finitely generated. Of course, then you can always find the subgroup with a finite index subgroup, which is torsion free. So if you have a torsion free group, then you can show that there's no fixed point here. Okay, so then you can find the finite subcover. So then M is good by the Selbach lemma. Okay, so it has no fixed point. Okay. So then M is a quotient of M tilde gamma, and gamma contains copies of the whole group. Okay. So M tilde is some kind of a leave here, so you can always consider this like this. And right, okay. Right. So actually, in that case, we can show that this M tilde, this finite cover, you can actually consider as a regular cover, where gamma is actually the a finite group. Okay. So using the Selbach lemma, because you can find the finite index normal subgroup as well, which is torsion free, because you can take an intersection of this torsion free group of finite index, which is still finite index. Okay, so that's a basic idea. So that's why people want to just consider the manifold, because it's usually going to be like that. So, but this G has to be a subgroup, a linear group. But sometimes it doesn't happen. But you need some kind of way to get around that as well. So usually most geometric manifolds are just going to be finite, covered by some regularly covered by some compact manifold. If you have a compact orbifold, but of course that's why they just want to study good orbifolds. But I don't see really why people should study good orbifold in the case of Kähler geometry and these kind of things, because Kählers are not geometric in this sense. Okay, so we don't really have any. I mean, this is only for a type of certain geometry. These types are only for that, not for Kähler and that kind of thing, or symplectic, for that matter. Right. So that's why we only study good person. The geometric people always want to do this, but uh, anyway, so then given XG structure, we can also get a developing map and the holonomy homomorphism. So you take a universal cover of M. So this is good. So you can assume that M tilde is a manifold. Then we can define a developing map to X by just finding the initial chart. Okay. So any modeling pair U can be sort of think of it being in M tilde. And then you continue by patching these together. Okay. And so you go to the next one. It differs by some element of rho, so you can move that rho by some multiplying by some G, and then you keep going. Okay. So you can just use some nice cover of M tilde and then extend. So the intersections are always there and that kind of thing. So then the map is well defined independent of which path of charge you took to arrive at given chart. Because this is simply connected, this happens only because it's simply connected. So if it's not simply connected, you will get different maps. Okay. So to see this, you just need to use some homotopy that because any two paths will be homotopic in the universal cover, so you can push one to the other, and then so any three of them intersect, then you can show the consistency and so on. Okay. So you need some induction to do that. So these are well written in Radcliffe, but for the manifold case only. Uh, so. So this is a XG structure on M tilde. So once you have this immersion, so D will be immersion to X. This will give you a XG structure because X itself is a XG manifold, and then you put you can pull back the actual structure using this D, because D is a chart anyway. So this will give you XG structure, and the covering map is 2M is actually XG map. Okay, so that's what the developing map is, and then what is a holonomy map? So it depends on which chart you start with. Okay, so any charts are actually depend on this initial chart, but the initial charts are only determined up to some action by G on the action by on the left, right? So all the developing map you can obtain is going to differ by some left action by element of G, right? So it will be like DG. Okay. So this will be DG. Any developing map will be. So you can change the initial chart to any K times rho for any C, so that the K circle D is another developing map. And you can see that any developing map is actually such a form because you can always take an initial chart or choose some base point. And from there, you can start from any initial chart, and then these uh, these are determined by the initial chart. Everything is determined by the initial chart. So therefore, it has to be like that. Okay. So given a deck transformation, we see that this circle rho is another developing map. So hence it must equal to H gamma circle D for some H in Z. Okay. So so H, then you can consider this. So for each gamma, you get a element of G. Okay. So therefore, there's a map from pi to Z. This is a homomorphism, so it's called the holonomy homomorphism. Okay. So you need to, of course, prove it's a homomorphism. So this is in the Radcliffe's book again, but of course you need they did it only for manifold, but the argument is very similar. So then this pair D and H is said to be the holonomy pair. Okay, so to define the holonomy, you need D. Okay, so D is involved in defining H. Okay. So, but so if you change D to some other thing, which is like G dot G circle D, then H will be uh conjugated like this. Okay. So that's again it's very simple to see, but you just need to verify this equation. Okay. So that's what you need to do. So to make this equal, okay, you need this. Okay. So that's so development pair is only sort of defined up to this G action. Uh, uh, and developing map and the holonomy homomorphism. So compulsory if you have developing map and the pair DH, then it will give you X charts. Because you can for any open chart you can leap to a component like this, and you can restrict it D to get that will give you X charts. Okay. So different choice doesn't really make any difference, and the local group is also the same. Okay, so development map also will define the XG structure. So that's converse. And then finally, we want to consider XG structure as a flat bundle with sections. So let's say XG manifold with X charts. Sorry, this is orbifold. Sorry, this should be orbifold. We form the bundle GM as above, and this is a principal G bundle. And in the orbifold sense, of course, we obtain a associate bundle XG using the G action of M. So what you do is you multiply by X, and then you act by G. So it will act right on the GM and then left on X. So this is how you define it, and you still can define this orbifold bundle over M using the fiber will now be X. Okay. And this is again a flat bundle because GM was a flat bundle. So we had this for each. So these leaves will define the flat connection, right? And this will again give you a flat X bundle. So in here, there's still going to be uh, uh, vibration by some X times the open set. So it will be fiber by this open set times X. Okay. So that will give you so locally it just looks like the X times U again with the action here. And then so foliation will give you foliation on X times C. So hence foliation on XM transversal to fibers. So this is a flat G connection, and so flat connection is always a way to identify fibers with fibers locally consistently, but it's only locally consistent. Okay. So that means in a model neighborhood, it's always going to come back to itself whenever you follow the connection. But if you on XM itself in the manifold, then so this will induce a flat G connection on XM tilde. So in the universal cover, it will also give you a G connection. So since this is a simply connected manifold, so M tilde is just X times M tilde as a X bundle. So it's a flat bundle, so you can always, for the simply connected ones, a flat bundle, you can always write it as a product, okay? So then XM tilde covers XM, and so XM is just this space made up by this action of pi 1 of M, this orbifold group. So connections will correspond to leaves of type X times M tilde in general, okay? So whenever you have pi 1 action, then since you're moving the product to product structure, so only thing that will change is the G direction or in X direction. So it will move by element of G. Okay, so for each gamma and pi, there's a corresponding action like this. Okay, so conversely, if you have any representation like this, you can build this product and then you act by this. And then you take the quotient. Okay, so then that will give you a flat X bundle over the orbifold M. Okay, so I'm just keep saying orbifold manifold, but it's really orbifold, right? Also conversely, an atlas of X G charts will give you flat X bundle with this section. So we can also get a section from the manifold to XM. I mean the orbifold M to the XM. So how do we do that? We have this developing pair DH. So you just choose a section by M tilde to X times M tilde just by using D. Okay, as a graph, right? So as a graph map. So X goes to XH. X DA at TX, X goes to X DX. Sorry, M goes to D M. So element of M, which is M, say goes to DM times M. Sorry, that's I got the reverse. Okay, so this will be transversal to the foliation that I talked about, like X0 X times M tilde in the differentiable sense. Okay, because this was these are always going to be differentiable immersion, so that's why it happens. And then you act by on the left on both. Then this will give you a consistent section from M to X M tilde. Okay, because it's equivariant property, you can get this transversal section. Okay, so from the axis atlas structure, you get this section. Okay, and so on the other hand, you can also get a transversal section like this. Then you obtain a transversal section from M tilde to X times M tilde. Then you can project to X and you obtain this immersion. Okay, so because it's a transversal, you can always get an immersion D to M tilde to X. So that D circle gamma is H circle gamma. Okay, using again these are taken quotient by these homomorphism H, so that this will be the homomorphism. So hence you obtain the development pair. So once you have this section, you can also get back to the XG structure. Okay, so let's see thing. So these three notions are the same. So hence given X charge, you get XG structure. Given a development pair, so given development pair, we define FC charge, so has XG structure. So given development pair, we define a flat X bundle with a transversal section, and given a section to flat X bundle, you determine a development pair. So these three classes of definitions are equivalent. So that's what we are going to use. Okay. So that's the first part of this lecture here.